Have you ever stopped to think about what a perfect inch or a perfect volt really is? For pretty much all of history, our answers to that were, well, surprisingly fragile. But today, we're going to dive into the absolutely wild world of quantum mechanics, where scientists have figured out how to create a truly perfect ruler, one that's not built from metal or some physical object, but from the fundamental constants of the universe itself. So, let's get into it.
Right, so that's the big question, isn't it? How do you create a measurement that's so perfect, so stable, that it's exactly the same for everyone, everywhere, forever? For centuries, the answer was basically, make a really, really good object and just tell everyone, hey, copy this. But as you're about to see, that whole system has a huge fundamental flaw.
And this really lays it all out. The old way versus the new way. On the left, you've got the artifact standard. Think of something like the Weston cell. It was basically a very fancy battery, the gold standard for voltage. But it's a physical thing. It gets old, its value drifts, and you constantly have to check it against some master copy somewhere. The best you could hope for was an accuracy of maybe 1 part in 100,000. Now look at the right, the quantum standard. This isn't based on an object. It's based on universal constants baked into the fabric of reality. It is perfectly stable. It doesn't change. And anyone, anywhere on Earth can reproduce it identically if they have the right gear. And the accuracy? We're talking parts in 100 billion? That's not just an improvement. It's a whole different reality of precision.
And believe me, this isn't just some abstract thing for scientists in a lab. This quantum leap had a massive real-world impact. In 2018, it was the key to redefining the kilogram. Yeah, the kilogram. For more than 100 years, the world's definition of mass was a literal cylinder of metal locked in a vault in France. Just think about that for a second. Our entire global system of science and commerce was tied to a single aging hunk of metal. Thanks to this quantum tech, we don't need it anymore. The last physical artifact is officially retired, replaced by a definition pulled from the laws of physics themselves.
So, how in the world did we pull this off? Well, it all comes down to one incredible, tiny piece of technology, a device that is truly the hero at the heart of this entire revolution.
Say hello to the Josephson junction. At its core, it's a deceptively simple idea. You just take two superconductors and create a tiny, weak link between them. But when you get the conditions just right, something amazing happens. It starts spitting out a stream of voltage pulses that are, and I mean this literally, quantifiably perfect. Every single pulse is an exact quantum copy of the one before it. There is no other device on the planet that can do this.
Okay, so let's break down how this little marvel works. It's basically a 3-step recipe. First, you get 2 superconductors. Second, you separate them with an incredibly thin barrier, something that isn't a superconductor. And finally, you hit this little quantum sandwich with a precise microwave frequency. And boom, the result is that stream of perfect, identical, quantized voltage pulses. It's like a tiny factory with a perfect quality control system built right in by nature itself.
Now here is the crucial part. The area under the curve of every single one of those pulses is always exactly the same. It's a value defined by one of the most fundamental numbers in the universe, Planck's constant. You know, that cornerstone of quantum mechanics that links energy and frequency. The exact shape of the pulse might wiggle a bit, but that total quantum package of voltage it delivers is always identical. It is nature's perfect, indivisible building block.
Okay, so you've got these perfect microscopic pulses. That's incredible. But how do you actually turn them into something useful? You know, something like a 10-volt standard that you can use to calibrate all the other instruments in the world. Well, that is the next giant leap in building our perfect ruler.
And this is the real engineering puzzle. A single one of these junctions, it's only putting out a voltage measured in microvolts. That's millions of volts. That's tiny. But the real world needs standards in volts, often up to 10 volts. So how do you scale up this perfect, tiny little quantum effect to a level that's actually practical for us to use?
The answer is actually a beautiful combination of brute force and incredible elegance. You don't just use one junction, you use hundreds of thousands of them. You link them all up in a series, one after another, kind of like stacking batteries in a flashlight to get more power. Their tiny little quantum voltages all add up to create one big, stable, macroscopic standard voltage. It's just a massive team effort.
But, and this is a huge but, it's not that simple. It gets incredibly difficult. As Dr. Sam Benz, who's a real pioneer in this field, puts it, you can't just toss them all together. The real challenge is making every single one of those hundreds of thousands of junctions almost perfectly identical. Why? So that, in his words, their quantum locking ranges overlap.
Which of course begs the question,
What the heck is a quantum locking range? Well, think of it as the system's operational sweet spot. It's this very specific, very narrow range of conditions. We're talking current, microwave power, temperature, where every single one of those junctions gets locked in to its perfect quantum state. As long as you stay inside that range, that sweet spot, the output voltage is perfectly flat, stable, and unwavering. You drift outside it, and poof, the quantum magic is gone. The whole game is about getting all those junctions to share the same sweet spot.
And here is the result of decades of brilliant work, the Programmable Josephson Voltage Standard, or PJVS for short. By figuring out how to make these massive, uniform arrays and how to keep them in that quantum sweet spot, scientists can now dial up any DC voltage they want, all the way up to 10 volts, with the unshakable, fundamental precision of a quantum constant. They actually did it. They built the perfect ruler.
But what if a perfect, stable, static ruler was just the beginning? What if you could use these perfect little quantum building blocks to construct not just a flat line, but any dynamic signal, any moving waveform you could possibly dream up? This leap from a stable value to a perfect dynamic wave is where this technology completely changes the game.
And that's where this thing called the Josephson Arbitrary Waveform Synthesizer, or JAWS, comes in. You can think of it as the world's most perfect digital-to-analog converter. It's amazing. You start with a digital code, a blueprint for the wave you want to create. That code tells the junctions exactly when to fire either a positive pulse or a negative pulse. Then, the system combines this perfectly timed stream of perfect little pulses to build your waveform, piece by piece. It's almost like a quantum 3D printer for electrical signals.
The output from this thing it's just hard to even wrap your head around how perfect it is. The signal it generates is so pure, the distortion is so low, that when scientists try to measure it with their best, most expensive equipment, they can't. The JAWS system is actually more perfect than the instruments trying to measure it. So instead of measuring the signal starts revealing the tiny flaws and imperfections inside the test equipment itself. It's the ultimate reality check.
So what does this incredible power let you do? Well, you can create signals that used to just be theoretical, something you'd only see in an equation. For example, a 1 kHz tone that is so clean, so pure, that its noise floor is more than 160 decibels down. That is an absurdly high-fidelity signal. You can generate a super complex chirp made of 101 different frequencies all at the same time. Or you can perfectly synthesize the complex QPSK signals that are the backbone of your smartphone and Wi-Fi. It's an unbelievable tool for inventing the future of electronics.
Now, this research has a legacy that goes back more than 40 years. But that very same perfect pulse, that totally redefined measurement, is now being pointed at one of the most exciting and one of the most difficult frontiers in all of science.
Today, that fundamental building block, that perfectly reproducible, quantized pulse that started this whole journey, is being used for a new task, a task that requires a level of precision and delicate control that is almost impossible to imagine.
And that task is controlling qubits, the fundamental building blocks of quantum computers. The very same technology that gave us the perfect volt is now being used to generate the perfect pulses needed to gently nudge and manipulate the super fragile quantum states of those qubits. It's a direct line connecting the world of perfect measurement to the absolute cutting edge of quantum computing.
So that leaves us with one last big thought to chew on. We've seen how one simple concept, a single, perfect, quantized pulse, has completely changed how we measure our world, and now it's helping us build the computers of the future. It's pretty clear that this fundamental building block, a gift from the laws of physics, is an incredibly powerful tool. And it just makes you wonder, with a tool this perfect, what impossible things are we going to build next?